Hello, everyone, and welcome to our today's Quanser user webinar. We invited Dr. Azad Ghaffari from Wayne State University to talk about the work in his lab focused on unmanned aerial vehicles and their safe operation. My name is Zuzana Fabushova, and together with my colleague Aryan Pana, we will be your hosts and webinar moderators today.
Thank you very much, Susanna. Today we have Dr. Azad Ghaffari with us. Dr. Ghaffari received his PhD degree in engineering science from University of California, San Diego. He's currently an assistant professor in the Department of Mechanical Engineering at Wayne State University in Michigan, United States. Dr. Ghaffari is known enough in the controls and robotics community, but just to give you a little background about his career and his industrial experience, Dr. Ghaffari, his career includes postdoc appointment at the University of Michigan in Ann Arbor and also University of California, San Diego. His work bridges the gap between controls, mechatronics, and energy systems. His research interests are control design for safety critical cyber-physical systems, distributed supervisory controller design for swapping modularity over smart networks, control of variable sample rate systems, high precision motion control of servo systems, aggregate demand response in power systems, extremum seeking and its application to maximum power point tracking in photovoltaic and wind energy convergent systems, as well as sliding mode control and linear matrix inequalities. He has 6 years of industrial training on control, automation, and instrumentation of combined cycle power plants, air-cooled condenser systems, biomass reactors, and multi-phase medium voltage synchronous generators and switching mode power supplies. I myself, and with the support of our local distributor in Michigan, had the pleasure to set up an autonomous lab for Dr. Ghaffari last fall in 2019. And today we're very excited to hear the results that him and his team have generated over the past few months using Quanser's advanced research systems. I'm sure you all going to enjoy Dr. Ghaffari's talk, but with all that being said, Dr. Ghaffari, the floor is yours. Looking forward to hearing your presentation. Thank you.
Yeah, thank you, Aryan. Thank you very much. And thank you for taking the time and showing up for this presentation. So today I will be talking about safe operation of UAVs using nonlinear robust control and modular barrier functions. So as Aryan pointed out, we basically did some of our work, including the experimental verification on the autonomous vehicle research studio by Quanser. The motivation behind this work goes back to the gradual integration of autonomous devices in human lifestyle. So with the increasing number of autonomous vehicles, including UAVs and self-driving cars that we see, so safety becomes a primary concern. So how to incorporate safety regulations into this driving cars or autonomous vehicles. So the objective of our research is to provide a scalable safety control for geofencing applications. So this mostly concerns at this stage UAVs. So we want to enforce a safe fly zone around a UAV, which is known as a geofence. And the solution that we provide is basically using modular barrier functions and in combination with nonlinear robust control to achieve the desired performance that we want. So mostly, as I said, we focus on UAVs, but also for the ground applications, we can implement geofences. For example, one obvious application is in delivery services. So if you have a UAV or a ground vehicle which you want to basically limit the movement inside a given area. For example, in these figures that you see, figure A and figure B, so the area which is confined between the red curves, that represents a geofence. So the geofence is basically represents a virtual net, which a set of distinct points. Basically, we have a set of distinct points, and then we want to maintain the movement of the vehicle inside the given set. And this becomes our operational environment. So the state of the art, the safety design, basically, there has been many different methodologies. So especially for UAVs, because we are dealing with an intrinsically unstable system. Also, the UAVs are underactuated. So that's the reason that creating safe trajectory is not an easy task. For example, you cannot just use the position or velocity information to maintain the vehicle inside the geofence. That becomes a tedious task. So that's why many people have opted out to enforce safety regulation at the control level. And popular methods that has been around from 1970s, early 70s, include, for example, barrier functions, which is a rather recent methodology. Potential fields, for example, dynamic programming methodologies. For example, you have MPC, model predictive control, quadratic programming, nonlinear programming. This all fall in this category, including as dynamic programming. And one other domain is basically machine learning, including artificial intelligence and other basically computationally intensive methodologies. So what are the issues with these methodologies? One is basically analytically, they are analytically complicated. For example, with potential fields, if you have a number of obstacles, or if you have basically an arbitrary shape geofence, that becomes quite tedious to create the control. And also basically they are computationally demanding. So that's why they require excessive human resources and processing power. So to basically to move ahead with our research, we selected barrier functions. They have some nice features embedded into them. So for example, you can use barrier functions in conjunction with Lyapunov functions to assure both safety and stability. So that's why we select to work with barrier functions. So having said that, there are some limitations to the barrier functions. For example, so if you have a given environment with number of obstacles, so you have to model the obstacles, your barriers, everything, so the boundary of your geofence as a control barrier function. So the control barrier function, loosely speaking, it has some similarities with Lyapunov functions. So for those who are familiar with Lyapunov functions, you know that how it is difficult to obtain a Lyapunov function for a specific application. So that becomes a little bit involved when you are dealing with a highly nonlinear system such as a UAV. So on top of that, the structure of the control is heavily enforced by the control barrier function. So that means we have low scalability. Depending on the number of obstacles, the shape of the geofence, you will end up with a different control structure, which means you have to modify this every time you encounter a new environment. So that means we have low scalability. On top of that, the methodology requires feasibility analysis, because in reality, we have system constraints, including actuator saturation, for example. That has to be done a priori. So what we propose here, we propose to basically use a modular barrier function, which basically provides a closed form safety control and basically limits the amount of analytical complexity and reduces the computational load of this safety control dramatically. So first, let's talk about the safety feasibility under control saturation. For this, let's just focus on a double integrator system. For example, we have we can model motion along translational axis or rotational axis using a double integrator. So that's why it's very useful to analyze the behavior of the double integrator. So let's say we have a double integrator, and the double integrator, the input, which basically represents the acceleration, it is limited because with any vehicle, we have a limited amount of acceleration and deceleration. So that's why we have limited the control between minus mu and mu. So now the safety requirement asks us to maintain the motion of the system such that h, x, and v always stays less than 0. So let's say in this case, we are interested in maintaining the position always negative. So we start with a initial condition with a negative position, and we want to see what is the required control signal to maintain the motion inside the safe set, meaning that we want to maintain the position always negative. So if you look at the figure that we have here, if you select a initial condition in the green, the shaded green area, so that means with the limited control actuation that we have, we cannot maintain the motion inside the safe, we cannot satisfy the safety requirement. And that's because of the limited control actuation we have, because that means if you are in the green, the shaded green area, you need a braking power more than mu to maintain the motion inside the in the negative range. So that's why we are dealing with a feasibility condition here. So if you do the math, you end up with a basically this feasible safety region, which is shown in blue here, and the equations are given. So any initial condition that you pick inside the blue region, so regardless of the location, so with the limited amount of control that we have, you can show that the motion will be always inside this feasible safe region. So we take this and we basically use it to build up our algorithm. So what are the goals and contributions in this work? So first of all, as I explained earlier, we want to enforce a safe fly zone on a UAV. And we have constraints on the system, including input saturation. We have under-actuated dynamics. Also, the equations of the system are highly nonlinear. On top of that, we have low-rate position measurement. For example, if you look at indoor application, even if you have a motion capture camera, the motion capture camera does not provide fast update measurement of position. It's at the rate of 100 hertz. And for outdoor application, when you have GPS or other basically measurement units, they have similar limitations, and also the precision that you can get from these devices, they vastly differ. So what we propose here, again, our methodology is based on modular barrier function. What we do, we basically incorporate the actuator saturation inside the modular barrier function. So the contributions that we have made here are twofold. First of all, we have proven the safety and convergence results analytically. So that means the results that we provide here, they hold for any sort of quadrotor that you have, and they can be also extended to ground vehicles. So, and the design also is scalable, and we have explicit safety control laws. That means the implementation of the control that we have here is quite easy, and it basically conserves the amount of processing power which is available to us. So the application that we are talking about is a unmanned aerial vehicle. As you see in figure A, this is the Q drone by Quanser, and the reference frames are shown in the in figure B. So as you see, we have the inertial frame and the body frame, and the details, I don't go into the details of modeling because you can find this anywhere, like if you have a good book on modeling, or even the papers, if you look on IEEE or somewhere else, you can find reasonable information about the modeling. So there are some basically properties associated with a quadrotor. So it basically the attitude, so the rotational, the angles basically, and the thrust, you can use them to control the translational motion. So that's one observation through the dynamics of the unmanned aerial vehicle. And the other thing is we can decouple the attitude and translational dynamics quite effectively. So with this, you can use a two-layer feedback linearization basically to decouple the entire equations of your system to 6 double integrators. 3 of them stand for translational motion, and 3 of them basically for the rotational motion. And as I explained earlier, the rotational motion is used to control the translational motion. So we use this properties to our advantage. So now that we have a bunch of double integrators, we go back to the double integrator. The problem statement is basically designed around solving the safety control for a double integrator. So consider the double integrator. Again, we have the input saturation, and the design requirement is basically to maintain, to obtain the safe limits on the control signal such that the position always is negative for all feasible initial conditions. So here, what we do is basically we incorporate control saturation into our safety barrier. So how do we do this? So as we explained earlier, the feasible safe set for the double integrator is given by a this shaded this gray area basically. So if you pick any initial condition in this gray region, so you end up on the dashed red line, which basically represents the boundary of the feasible safe region. So if you pay attention to this, the barrier function here, if you end up on the dashed red line, which, as I said, it shows the barrier function, the motion does not stop at the origin, because if you are on that dashed line, it means you are constantly braking. It means you are continuously braking, and there is no chance that we can stop at the origin. So that means, so we have solved some of our issues, meaning that we have a feasible, safe set figured out for our double integrator. But now we have another problem. So if we arrive on the barrier function on the border of our safe set, we do not stop at the origin. So what's the next step? So we have to modify this barrier function to achieve stability, meaning that if we arrive on the barrier, so we want to make sure that the system stops at the origin. So to achieve this behavior, so we change the input comment proportional to the position. So as we get closer to the origin, we reduce the control comment. So this is given as a tan hyperbolic equation, as you see here. And if you do the math, basically you end up with the modified shape of the barrier function, which assures the convergence to the origin. So here we have a additional parameter rho, which is introduced here. It's a positive value. It can get very close to 0. So if you get very close, if you make rho very close to 0, it means you can get basically the you get to the red curve, which basically represents the constant breaking power set at minus gamma. So that's not what we want. So that becomes another design factor here. So we have to design rows such that we get the performance that we desire. So with this information, so we have input saturation embedded into the barrier function. We also have the convergence property embedded into the barrier function. Now we end up with the barrier function for the double integrator as shown here as B, X, and V. And please note here that H is the unit step or the Heaviside function that we have used here. So if you look at this barrier function, it is continuously differentiable. So that's quite useful when we basically derive our safety control law using this barrier function. So this barrier function actually gives us decreasing control command when we approach the origin. So that's the reason that intuitively, that's the reason that basically we can guarantee convergence. So now to dig deeper into the analytical the proof of convergence and safety, basically we introduce the barrier certificate functions. So these are a certain class of barrier functions. So let's say that you have a dynamic system given here as dz over dt equal to fz. So this is a arbitrary system. So if we have a function phi z, we call it a barrier certificate function with exponential decay rate if it satisfies these three conditions that we have presented here. So first of all, phi has to be differentiable with respect to z. Second, phi z at the initial condition, phi z 0, has to be negative. And the third, the derivative of the time derivative of phi along the dynamics of the system has to provide an exponential decay rate. So if these three conditions are satisfied, then we are dealing with a barrier certificate function. So if you have a barrier certificate function, you can basically use this lemma presented here to show safety, basically to prove safety for a given system. So if you have a barrier certificate as phi z, and if phi z 0 is negative, then you can prove that phi z stays negative for all time larger than 0. So this is basically very useful because we have already figured out a barrier function, and it turns out that the barrier function that we have already figured out, it is actually a barrier certificate function which satisfies all of these properties. Now, because we have these properties, we can use this lemma actually to show that to derive our safety results. So again, we have the input saturation, which is U between minus mu and mu. And we have B as our barrier certificate for the double integrator. And we have a safe set omega, so which is basically this the set that we were talking about. If you look back here, the gray area, the shaded area, that is our safe, that represents our safe set. So now with this information, we want to see what is the control law that maintains the safety of the system for all the initial conditions inside the safe set. So if so, we have shown this that if you have an initial condition selected inside the safe set, and the parameters that we have, gamma is positive, obviously less than mu, alpha positive, rho positive. So if you have the control command less than US, which is given in this closed form expression here, then the set omega is forward invariant for all t. That means any motion that starts inside the safe set remains inside the safe set forever. So also above that, you can also prove that the command, the US, the limit that we have, it is always up larger than minus mu. So this is very useful when we basically go to the next step. So the next step, basically, so what is with this result? So we have a safety verification result. We can say that if the control command is less than this limit, then we are safe. So now how can we use this for basically in a trajectory tracking application, for example? So let's say you have a control as you are, which basically is designed to track a reference trajectory as XR. So with this, you can, the green box that you see here, the control command, which is shown in the green box, basically, if you implement this control command, you can assure that you always have safety, and as long as the reference trajectory is inside the safe set, you have accurate tracking. And please note that we have a saturation function, which basically takes care of the saturation, applies saturation to the control command, and the saturation function is defined in the bottom of this page. So what are the benefits of this control? Again, please pay attention that this is a closed form control signal. So what are the benefits? So first and foremost, we have a closed form expression for our control signal. So we already know what is UR because we can use some available methodology to design UR to track a reference trajectory. Also, from our previous theorem, we have the safe control limit, which is U of S. So that means everything is known in this control comment here, this control law here. So, and the interesting part is with the control, with the safety control, we only have 3 control parameters. We have gamma, we have alpha, and we have rho. So that makes the tuning and calibration extremely easy. And on top of that, we have a scalable design here. We have the closed form solution, and we have the limited parameters, which makes the design very scalable, easy to tune and implement on an actual system. So this was the base module for our entire design. So we have shown that we have a control, closed loop, closed form control that guarantees both tracking and safety at the same time. So now let's use this to create more complicated scenarios. So let's say, for example, you want to maintain the motion between a low and high limit. So as you see in this figure, we have X low, X high. We want to maintain the motion of the vehicle inside this shaded area. So if you do the math, you end up with the safe set as given here. So BHBL, again, you can find the expressions for this red and blue curves using the the barrier certificate function that we found in the earlier step. So now with this configuration, so this is the final shape of the control that we come across. Basically, if you look at this yellow box here, you have two saturation nested here. So one is basically the outer saturation is the basically represents the actuator saturation. That's there. You cannot do anything basically about it because the actuator is basically providing limited comment. So we have the outer saturation function representing the actuator. We have the inner saturation function, which basically represents the safety law here. So the safety law, we have UL, we have UH. So this, guys, UL represents the basically the limit, the low limit, and UH represents the high limits. And again, we have closed form solutions for UL and UH. And in the inner, the most inner, basically, part of this equation, we have the reference tracking. So the reference tracking, as you see here, we did not limit the structure of the reference tracking, the trajectory tracking algorithm. It could be anything. So that's the beauty of this design. Basically, you can have any reference tracking algorithm, and you can basically augment this provided safety law here into your design without worrying about changing your trajectory tracking algorithm. So with this information, I just want to also elaborate a little bit on the selected methodology that we have used for trajectory tracking. So again, because of the complication of the system, the system is under-actuated, we have nonlinearities. We have selected super twisting algorithm to design the reference tracking control. And because we showed that it is possible to transform the dynamics of the UAV to a bunch of double integrators, it's enough just to study the problem for the double integrator. So this design is applicable to the basically the position control, which is basically the translational motion, and also the rotational motion. So if you look at this again, another basically benefit of using the super twisting algorithm. So this is a high order sliding motion. Basically, you can enforce that you get basically your variable is zero, and the time derivative is also zero. So that means that you have a smooth transient, and the behavior is very robust. So if you look at this green box here again, you see that this provided control is actually only has three parameters. Namely, we have lambda, K1, K2. So again, we have three parameters for the trajectory tracking algorithm. We had also three parameters for our safety control. So that means we are dealing with a limited number of parameters when it comes to control tuning and calibration, which makes the implementation much easier. So with this, we come to the basically the summary of our control design. So we have the quad rotor, which is under-actuated, but again, it can be actually decoupled into a number of double integrators. We have 6 degrees of freedom, 4 actuators, and we use a 2-level feedback linearization to convert this dynamics of the system to 6 double integrators. So this was instrumental in our basically control design. So attitude and thrust, we use them for trajectory control, and roll and pitch and yaw torques are used for attitude control. So one other important factor here is to basically to design the attitude control loop much faster than the trajectory tracking loop, because with the quadrotor, it's all about maintaining the rotational motion. So at the desired level, if you have it controlled at the desired level, it means that you have a basically desirable translational motion. So our proposed design, which is a modular design, allows us basically to use the similar safety control structure for all the translational axes. So that's very important. So if you have one control the design for one of your translational axes, you just basically can copy paste to the other axis to get the performance that you desire. So the structure of the system that we have designed is presented here. As you see, we have the UAV, we have position, linear velocity, angular velocity, angle, all of these measurements are available to us. We have the trajectory control in this orange box here. And we have the attitude control separated from the trajectory control. And also, please pay attention that the safety control is completely decoupled from the trajectory tracking and attitude control. So that means, so it's true that we use the super twisting algorithm here, but you can use any other methodology to design your trajectory tracking or attitude control. So as a matter of fact, actually, we did this in our lab. We used the for example, PID design. We use also integral sliding mode control. So, and we also implement a super twisting algorithm. So all of these designs, basically, they do not change the structure of the safety control. So again, to get the desirable performance out of our system, we set the attitude control 5 times faster than the trajectory tracking algorithm. Basically, the inner loop has to be faster at least 5 times than the outer loop. So this is the hardware configuration that we have used for our system. So as you see, we have the quadrotor, we have the motion capture systems. So because of the size of our lab, we have 8 motion capture cameras here. So these motion capture cameras are connected to our ground control station through a USB connection. And the ground control connection basically is communicating with the quadrotor through a wireless router. And please pay attention. So in some cases, for example, when we are dealing with micro UAVs, so some people, they just do the calculation in the ground control station and transfer the commands via Wi-Fi to the quadrotor. But here, everything is done on board the quadrotor. So the ground control station is merely there to collect data from the system and to modify the control algorithm. So as I said, this is a real-time implementation. The control loop runs at 1,000 hertz, and the motion capture, as I also explained earlier, it runs at 100 hertz. Basically, that is the highest rate that you can update the position information. Also, we have onboard IMUs, and we use this the combination of the motion capture and onboard IMUs through a complementary filter, a set of complementary filters, which was provided by Quanser to get the basically position and rotation motions informations from our system. So what we did to implement our control design, we went through a empirical calibration, basically a number of iterations to get the desirable result that we want. And we made sure that the attitude control has a fast, accurate, and robust behavior, which basically is critical to get the performance for trajectory, to desirable performance for trajectory tracking scenarios. So we designed 2 main cases here. So we have one pilot produced reference trajectory, and we had another case which is basically a smooth reference trajectory, which basically which means that you have a reference which is within the design criteria, and we use this basically to see what is the accuracy of the reference, the trajectory tracking, the attitude control behavior. And the pilot produced the reference trajectory. We mainly use this experiment to verify the robustness and the robustness and the safety of the proposed control design. So this is the first experiment. As you see in figure A, you have the dashed, the dotted black line. Basically, that is the reference. And as you see, please pay attention again, we have set the altitude at 50 centimeter. We don't change the altitude. And the reason is basically we want to see what is the robustness of the altitude control, because that's also another important factor when it comes to the control design for a UAV. So what we did is basically through the wireless joystick, we changed the reference in X and Y direction. And the changes that you observe here is beyond the control design criteria that we have. That's why you see that the actual position of the UAV lags behind, because the reference is changing dramatically. And this, although that the reference changes dramatically, you can see that the motion of the UAV is maintained within the safe zone here. And you see that X staying within plus minus 35 centimeter, Y the same. And we do not violate this the safety criteria. And again, if you look at the figure B, that basically also provides the effect of the safety control that we have. So technically speaking, the safety control that we provide here, it controls the acceleration of each translational axis. So if you look at the cases that the reference goes above, beyond the safety limits. So you see that our proposed methodology basically crops the acceleration at the safe level. So you see the green line here shows the unsafe level of the control command, which is provided by the trajectory tracking algorithm. But our proposed safety control crops this satisfactorily to maintain the robot inside the safe zone. And on top of that, if you look at the performance of the altitude, you see it is quite robust, regardless of the changes that you see in X and Y. Z stays almost without change. It stays at 50 centimeters. So this is very assuring for us. We see that this performs very accurate and it is robust. So now the second experiment that we conducted, we basically designed a box around, it's a virtual box around the robot. So we have the limits for our geofence defined as X less than, between minus 135, the same for Y, and Z goes between 0 and 75. And we changed the reference. Basically, the reference here is within the design criteria. So the reference changes accordingly, as you see here in figure B. So during time 10 to 35, the reference is outside of the safe zone. But regardless of this, basically the proposed safety control keeps the robot inside the safe zone, inside the geofence. And basically, if you look at figure A, which shows the spatial variation of UAV position, you see that the reference basically is outside of the geofence, and the robot actually shadows the reference trajectory on the border of the geofence. And on top of that, we have a tracking accuracy above 95%. So that's quite good, actually, for if you compare it with any other algorithm trajectory tracking. This is very good. We have above 95% accuracy. So similar with the previous case, if you look at figure A here, in the situations that you have the reference outside of the geofence, you see the provided safety basically crops the acceleration along the translational axis to maintain the motion inside the geofence. And also another thing is, if you look at the roll and pitch angles, the behavior of the inner loop, you see it quite instantaneously follows the changes of the roll and pitch. That's very fast and accurate, actually, because the RMS error for roll and pitch is within 0.74 and 0.55 degrees, actually. It's quite remarkable in terms of performance. And also, please pay attention that because we have set the yaw angle to 0, it's not shown here. So roll and pitch are the only angles that we have changed here to maintain the desirable behavior that we have. So to conclude our talk here, so we provided an expression for feasible safety barrier incorporating input saturation. It also incorporates a convergence to the origin. So we have used this barrier certificate function to obtain a closed form safety control law for the system that we have here. And this is a modular process. Basically, we created the base module for one axis, and then we use this for the other axis. And that means that the design is quite scalable, and it is easy to tune and implement. So also on top of that, we provided the proof of safety and convergence. And the results that provided here, basically, it has been already published in ACC 2020, and or most recently, the extended version has been published in IEEE ASME Transaction of Mechanical Mechatronics, sorry, and you can find the article, both of them, on the IEEE website. So our current effort basically focuses on developing these results for safety sets with time-varying boundaries. And for the case that there are multi vehicles involved in this scenario. So I think at the end, I would like to thank many people who were involved in this project. So this wouldn't have been possible just by me or my team only. So we have Wayne State University and the Department of Mechanical Engineering to thank. Basically, these guys, they provided the seed grant to establish the lab and the environment, actually, the safe environment for us to do our work. And also, I would like to thank our student assistants, Mr. Bilal Mohsen and Ms. Farinaz Nizam Pasandarbabi. These guys, actually, they did a wonderful job. During the preparation, installation, Bilal helped to conduct the experiments. Also, I would like to thank Quanser, especially Aryan, Mortaza, and John. These guys were very accommodating. They helped us to install this setup very quickly, very efficiently. And last but not the least, also, I would like to extend my gratitude to wonderful people at ATS Midwest, especially Chris Roberts and Michael and William also. These guys, they did a wonderful job. And again, at the end, if you want to learn more about our work, our team, please go online, look at our webpage. And if you have any question, if you need more information, please don't hesitate to contact me. Thank you very much.
Awesome. That's great. You're very welcome, Dr. Ghaffari. Thank you for your amazing presentation, and thank you for giving us this opportunity to set up the lab for you. It's a pleasure, and we're looking forward to our continued collaboration and relationship with you and Wayne State University. So some questions actually have been sent to us, and I want to go through them. And hopefully we can cover all of them within the next 8-9 minutes that we have. If not, then all the attendees, they can reach out to Dr. Ghaffari, send him an email, and he will respond. So Dr. Ghaffari, they're asking that on slide 8, does two-layer feedback linearization for the quadrotor involve an inner loop and outer loop for translational and attitude control?
Yes, that's correct. Yeah, we have an inner loop for the rotational motion and an outer loop for the translational motion, basically. And that's what I explained further in this slide here when I talked about the super twisting algorithm. And the same design has been used for rotational motion and for the translational motion. And if this is basically, this is the structure of our design that you see here. And yes, the inner loop represents the attitude control, and the outer loop represents the trajectory tracking control.
Amazing. And next question is about slide number 9. It is mentioned that a feasible initial condition is required for the methodology to work well. Could you give an example of an infeasible initial condition?
So let me find the slide 9 here. So slide 9. So the infeasible initial condition, please, if you look at this slide 10, for example, one infeasible initial condition, or actually any initial condition that goes above this red curve that you see here. So that becomes an infeasible initial condition because you don't have enough control common to bring this this system back into the safe zone. So any initial condition which is above this dashed red line, that is considered unsafe.
Awesome. Sounds good. If there's any follow-up question, please email it to Dr. Ghaffari, and he will respond back. So the next question is, would there be a preferred trajectory that the quadrotor can follow while braking and remaining within the boundary so that the minimum power/energy is utilized? How would this optimization affect the control system design?
Yeah, that's actually a very good question. So that could be accommodated within the trajectory tracking control, actually. So we can keep the safety control as it is. So as we discussed this earlier, and then you can actually implement your desirable methodology. So for example, if you have a optimization based, you want to minimize the energy, so you can put that into the trajectory tracking and attitude control, basically. So meaning that instead of, for example, super twisting algorithm, you can do optimization based for your attitude and for your translational control design.
Perfect. Next one is, how do you overcome or test the conservatism of the robust control design?
So again, this is another good question. So the conservative design that you are dealing with, so here actually, so it is mostly with the, it is mostly with the unknown factors that are involved in the system. So if you look back into the basically the super twisting algorithm for the second order system, so there is a factor here, delta. So that basically includes the uncertainties, unknown dynamics, which is bounded by m. So yeah, that's true. So if you have a very conservative approximate of M, so that affects the whole design here. So one way actually to alleviate this issue, maybe you can do another, like for example, optimal version of this design, or replace this basically to estimate the upper limit of delta as you go. Or another way is basically to conduct an empirical analysis of your system to see what are the limits that you get on M for each axis. So that one you can accommodate. As I said, I think the easiest method is opting out for an adaptive design. For example, some people, they have used backstepping. It is very actually efficient, very useful. There are some good results on backstepping. So the other caveat with backstepping, for example, or any other adaptive version of this designs, basically you risk adding complexity to your design. So if you make your design more complicated, again, so you have to see where are you standing. So if that is something that you can afford, yes, by all means, you can use an adaptive version of this design, or something, for example, like backstepping, which also has been has been proven very effective.
Awesome, sounds good. The next question is, how does the system handle the disturbance, the external disturbance?
So the external, that's another good question. So actually this project, we did not focus on external disturbances. So that is among our next basically steps. That would be addressed in our upcoming projects.
Great. Great. Next one, since you're using PID controllers for controlling the quadcopters, I'm assuming you're using the linear models for the quadcopters. Have you applied your barrier control?
We don't use PID controllers. So as I said, we used initially PID controllers to show the effectiveness of our proposed safety control. So that worked. It was acceptable, but the performance, basically the accuracy that we got from PID, it wasn't there. So that was the reason that we opted out for a more sophisticated control design, and that's what we that's where we decided to use the super twisting algorithm. So right now we are using the super twisting algorithm, which is given here. The details, you can find it in the papers. So, but we did not use PID here. This is for super twisting algorithm.
Perfect. Thank you very much. The last question, on slide number 22, how is the bound on acceleration obtained? Is this a reference acceleration that the UAV must follow to track the reference trajectory?
No, so the bounds that you see here, the red bounds, if you, for example, look at figure B, the top one, UX, for example, you have two bounds. One is for basically low bound, one is the high bound. So the way that we obtain these limits is basically through this, the nested saturation function that we provided here. So please, if you look at this big yellow box here, you see UL and you see UH. So UL and UH, we have this relationship US, which we basically provided in this slide again. So this is how we get the upper limits on the acceleration. So this is all done using this safety control design.
Dr. Ghaffari, thank you very much for your time and for your great presentation. It was great to hear the results that you and your team have generated, and we are excited and looking forward to hearing more about what's coming out of your lab. And I want to thank everyone else who joined us today and attended the webinar, and hope to see you all next time at the next webinar. Thank you all.